Welcome to our lectures on advanced power electronics and control. Today we shall discuss about the another important entity of the power electronics, that is DC to AC conversion, and we shall discuss about power electronic circuit. So, we shall discuss about voltage source converter, voltage source inverter and the current source inverter. Process of converting DC voltage into the desirable repeating voltage is called the inversion, and it can be of two type. One is actually this based on the topology, and source are maybe voltage or current you want that feed it by the inverter, and we shall see that what are the different kind of constraint and the applications of the voltage source converter and the current source converter. Inverter are essentially classified into the two basic type based on the utilizations of the commutation technique. Previously, since power electronics comes into the pictures with the advent of the thyristors, so these two terms were quite important. So, we require whether it is actually it can be commutated by the external commutation circuits. So, you require to have a external commutation circuits to be placed to commutate it, or it can ensure the natural commutations, like in case of the conversion. In case of the conversion DC to AC, thyristors are line commutated. Can we have some kind of thing like that? So, that is called the self commutation. And now external commutations we have actually studied in the different kind of communication technique for the thyristors. Mostly auxiliary commutation of the thyristors are being employed in case of the thyristors. Otherwise, if you have a GTO, you have to have the negative pulses to withdraw the devices. Inverters in switch and the energy required to turn SCR provided by the external motor or the power supply. So, that is basically the external commutation. Basically, it is not possible that load which will provide the proper counter voltage for the commutation, because you know there is a different kind of technique for the commutations of the thyristors. You apply the reverse voltages and you bring the current below basically the voltages, below the actually the holding current. If it cannot be done by the load, because for example, if you are feeding a leading power factor, then what happens, current actually goes 0 before voltage goes 0. So, it can be naturally commutated. So, it does not happen sometime, then we have to see that we have to externally do it by auxiliary commutation. Basically, it is not possible to guarantee that the load always provided, because load is something that actually it is a user's choice, not designer's choice. So, it will offer you the commutation. Then a self commutation, and if it is ensure that the load can provide the process of commutation, then we employ the self commutating inverters. And these inverters can be actually used for, if it is self commutation type, then actually we can withdraw by the gate pulses. These are essentially GTOs. It has the highest power rating and the lowest switching frequency. IGBT is the middleman in the row, medium power rating of the tens of kilowatts and tens of frequencies. And power transistors we nowadays not use, because power dissipation is quite high, but you can use the MOSFET which have a higher switching frequency, but lower power rating. So, we have a different kind of inverter depending on the source. Source can be voltage and you are feeding to the load, then it is called voltage source inverter. Similarly, you can have a current source inverter, and you will see the different kind of control technique for those inverters, and most suitable method is the pulse width modulations, mostly for the VSI. For you can use it, and we shall discuss in details for applied to the both the cases, and we will see the advantage of the pulse width modulation over other different kind of converter inversion operation. Now, the shape of the ideal VSI voltage waveform should be independent of the load connected to the inverter. So, this is the desirability, because it will mimic the characteristics of the rigid grid. So, that is the desirability of the VSI. It will actually give you the desired voltage independent of the load connected to it. So, so this inverter output voltage should not be distorted by adding or withdrawing a different kind of linear or the non-linear load. So, application of the VSI includes adjustable speed drive. Why adjustable speed drive? Most of these actually motors are induction motor nowadays, and thus they are close to their synchronous speed, either near to the 1000 rpm if it is a 6 pole machine, if it is a 1500 rpm it is a 4 pole machine. But if we require an adjustable speed drive with a wide variation of the range like modern leaps, elevators, all those things, then what should we do? So, we require to actually have a power electronics supply that will give us variable voltage and the frequency. So, there VSI finds its applications. Uninterruptible power supply, it is very common use in case of this basically our desktop kind of application, desktop and applications. So, we provide actually power backup. Once power is off, then it is called as actually offline UPS. You can have a online UPS, because if you want to have a process power, then you actually once power is there, you will take power from the grid and you rectify it through the power factor rectification technique, and it feed it to this actually the inverter to give a process power. So, that even this utility provides you that the dirty power that is get corrected, and once power is off, that will give the voltage from the battery, and if there is a brownout condition, it will actually give you the compensated voltage or the sag voltage. So, in those application also we use voltage source inverter, and thereafter we have active filters. Active filter essentially what does it do, due to using these entities, we basically distort the power quality. Power quality is a very big term. Power quality essentially two important entities of the power qualities are power factor and THD. So, these are two entities that actually affected because of this adjustable speed drive and uninterruptible power supply and other different modern power electronics devices. Active filter essentially a solution provided by the power electronics to this problem, where you actively mitigate the harmonic and you improve the power factor, that is called active rectifier. And thereafter we have a flexible AC transmission system, that is FACS. So, it has a whole gamut of solutions. These are series compensation, shunt compensation, shunt and series compensation, angle compensations. So, all those things we generally find VSI, and the voltage compensator and the also photovoltaic inverters, solar photovoltaic inverter is also a type of the VSI. So, let us see that what is this is the simplest form of the inverter. It is in a bridge configuration, and you can first we assume that load is highly inductive. So, there is no challenge involved if load is resistive. So, voltage and current will be in a phase and thus you do not have much problem. But if it is a lagging kind of aspect is there, voltage is lagging, sorry, current is lagging the voltage by 90 degree, then you will find that current is at peak when you require to switch it off. So, that is something the worst case condition, and we require to actually take care of those aspects. So, this is the Vs by 2 and this is the voltage applied once Q1 and Q2 is on. So, voltage AO will be essentially the half of the actually the supply voltage, and voltage BO will be the actually the negative. If you combine, then it will be a line voltage AB between these two, and you will get the full Vs, and you will see that actually this is the square wave is the voltage applied, and we assume that current is highly inductive, and for this reason you will find that current is been phase lag by angle theta. And always remember, I said to you that basically try to decrease the value of the current, whether it is a positive cycle or negative cycle. So, even if ramp is positive, please see that magnitude of the current is decreasing. So, then always you remember that the diodes are conducting. So, it sets the prelude to the actually the switches to the operation. So, when you can see that when it is ramping on in a positive direction, so of course, that Q1 and Q2 require to actually bring it up. Till that time, once it is not switched, so D1 and D2 will come into the picture, and this will actually try to decrease the current and will try to close to the 0 value. Thereafter, Q1 and Q2 has been triggered, and that will ramp on this current straight away. And here at this moment you basically withdraw pulses of Q1 and Q2. Then, but since the current is basically cannot change its direction instantaneously, so current will continue to flow, and you will find that, so instead of the Q1 Q2, current will flow through the load through basically D3 and D4. So, this will be the path for the current. Now, once D3 D4 is been conducted, so I have always said once diode conducts, current falls. So, ultimately current will gradually fall. Once it close to 0, you are supposed to turn on your another pair of switches Q3 and Q4, and that will be continued and so on. So, this is called the square wave operations of the inverter for highly inductive load. So, same thing can be extended for the 3-phase 3-US system for 3-phase inverter. Since the power transistors are self commutating, no special commutation component are included in the circuit. So, you will be using GTO, IGBT or power MOSFETs, and so if you like to use actually the thyristors, then you require to incorporate the auxiliary circuit for the commutation. There are different kind of auxiliary circuit, and it is been named by the name of the inverter like Mac-Bedford inverter. We used to study in when our BTech days, but now gradually it is phasing out with the advent of this actually this modern switching. Since power transistors are self commutating, no special switch is required. In this circuit, the transistors are made to conduct, and so that you name it in such a way that actually the switches S1, S2, S3, S4, and you can give it because you should have this subtraction and gives you 3. Then you can see that consecutive switches will come into the picture. If it is S1, this will be S4, if it is S2, this will be S5, if it is S3, this will be S6, and we shall assume the same thing, we are feeding highly inductive load. Now, we have a different mode of conduction. One switch will conduct 120 degree, and we will see that another mode 180 degree. There are two types of control signal can be applied to the transistors, 180 degree mode of conductions and 120 degree mode of conductions. In case of the 180 degree mode of operations, each device conducts whole cycle of whole half cycle, that is 180 degree. And sequence of firing, you will find that actually S1, if it is triggered, you will find that 3 devices will conduct at a time. So, you will find that S1, S2, S3 or 1, 2, 3, 1, 2, 3 will conduct 1, 2 and 3. So, ultimately this will conduct initially. Thereafter next sequence will come, that is 2, 3, 4. Thereafter 3, 4, 5, 4, 5, 6, 5, 6, 1 and 6, 1, 2. This as the sequence will gradually follow, and we will find that first 2 thyristors 1 and 3 or the switches from the upper legs and 1 in lower leg will conduct. Thereafter actually 1 will be the outgoing thyristors after 180 degree. So, 2, 3, 4 will conduct, incoming thyristors will be 4. So, there will be 2 thyristors from the lower leg and 1 thyristor will be from the upper leg. Similarly, this will be follow again, there will be 2 thyristors from the upper leg, because odd number are upper and the even number are for the lower leg, and getting signals are shifted from each other by 60 degree. For this, for 120 degree mode of conductions, each thyristor conducts 120 degree, and sequence of firing will find that 6, 1, thereafter 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1, again it will be repeated thereafter. So, first of all 6, 1 and 6, thereafter 1, 2, thereafter 2, 3 and so on, consecutively it will carry on. So, here you can see at a time 1 thyristors or the switches from the upper leg and the another from the lower leg, this is for the lower leg and this is for the upper leg, will conduct. So, let us see different kind of mode of conductions for 180 degree mode of conduction. So, each thyristors individually will conduct for 180 degree. So, this will start and the stop time of the switch T1, and this will be T4 and this will be again T1. So, after actually we can see that before that T5 was conducting, and when T1 comes into the picture and T3 was conducting. So, you can see that at the interval what are the devices are conducting. So, you can see that is T1, T2, T3. Thereafter, you can see that T6 comes into the picture, then T1, T2, T6 and subsequently those series will come. So, Vs will be actually the Va will have this kind of pattern, and thereafter you will get Vb, that will be a 120 degree phase shifted, and similarly you will have Vc. So, that will be 240 degree phase shifted or 60° leading. Now, if you subtract this, you essentially will get the line voltages VAB, that is 2 Vs, and this will be this kind of nature, and so it will be steps. And similarly, it will be actually for CA, and similarly it will be for BC, and it will be for the CA, both will have the same relations of the same phase shift. So, these are 3 line voltages and these are 3 phase voltages. Now, you can see one thing. So, if you can see that, so this voltage is essentially is the 2/3 of the DC bus voltage, and this is basically the neutral voltage, line to neutral voltage. So, you will find that the staircase voltage line to neutral in case of this 180° mode of conduction. Similarly, this voltage will be actually VDC by 3, there are 2 VDC by 3 and so on, and same staircase kind of profile will be followed if it is actually line to neutral output voltage for unground star connected load. This will be the profile, you will get it in case of the phase voltages. Now, let us see that the conductions for 120° mode of conduction, this is G1, G2, G3, G4 and all the pulses, and switches will conduct for the period of 120°, and there will be a phase shifted, all these pulses will have a 60° phase shifted. G1 and G2 will have a 60° phase shifted, and these are the gate pulses, and corresponding switches will be actually T1 or S1 as you have seen. So, this is T2 and T3 and so on. We assume that this will conduct for the same durations of their respective gate pulses. So, this is basically the neutral voltage, and ultimately you will see that when it is on, upper thyristors was conducting 1 and lower thyristors 6 was conducting, and thus you will get this voltage till 120° time. After that, once T1 is off, then you will not get any voltage across the VAN. Then again after an interval of pi by 6, the lower thyristors T4 is triggered and you will get minus Vs by 2. Similarly, in this case, the lower thyristors was conducting for the phase B, that is basically the 2, thereafter it will be off for the period of actually 60°. Then at this moment actually T3 will be actually switched on and it will conduct till the time of another 120°. Similarly, this will be basically the case of first T6 is been switched on, thereafter actually T2 is been switched on, thereafter this is a case of T4 been switched on. Now, harmonic analysis of it. So, what should be the RMS value of the output voltage, since it is an AC, we are interested to find it out this AC RMS value. So, we require to integrate over it 2 by pi 0 to pi V square ddt, and you will get essentially the value is equal to Vs. And now we require to find it out the individual components. So, we can find it out since there is a symmetry involved. So, only odd harmonics will be present. So, we have a harmonics that is 1, 3, 5 so on till infinity. So, the fundamental RMS output voltage is V01 RMS 4 Vs by pi root 2 equal to 0.9 Vs. For an load, the instant load current is, so you can actually integrate over it, 135 to infinity 4 Vs n pi under root r square n omega L square sin n omega t minus theta n. So, this is the basically essentially you divide it by the load, you get the load current. So, basically this inductor component will change and offer a different kind of impedance for different kind of different frequencies. So, it will be actually this nature. Now, what should be the line voltage? Generally what happens, this is the average value, it should be 0. So, we assume that there is a exact symmetry involves and we do not have any DC value, and from the symmetry we know that actually the cos component will be 0, we are left with only the sine component. And so, we can see one thing that till minus 5 pi by 6 to plus 5 pi by 6, the voltage actually for the phase A is minus Vs. Thereafter till this value it is positive. So, you can calculate, and while by integration the value of BAN will come out to be 4 Vs by n pi, where n can be any integer sin n pi by 2 sin n pi by 3. So, this will be this basically the Bn. So, what should be the value of AB? AB will be essentially you subtract. So, you will get 135 0 to infinity 4 Vs by n pi sin n pi by 3 sin n omega t plus pi by 6. So, similarly you will get these values are 120 degree phase shifted. So, this value will lead the phase value by 30 degree. So, it is plus pi by 6, here it is instead of minus 120 it is pi by 2, and here it is another phase shifted by 120 degree, that is 7 pi by 6. So, this will be the expressions of the 3 voltages. Now, harmonic analysis. So, what is the amount of the harmonic present into the system? So, line to line voltage, RMS value of the component. So, VL, of course, this voltage across the inductor you can integrate over it. So, 2 by 2 pi actually you will know that it will conduct for the period of 2 pi by 3. So, V square by V square S ddt half. So, this value will be root 2 by root 3 into Vs, that is 0.8165 something like that. So, similarly RMS values for the nth component you have to actually for the nth value, and you will get 4 Vs by under root 2 n pi sin n pi by 3. For n equal to 1 you will get V1 equal to this value. So, line to neutral voltage Vp will be essentially VL by root 3 is basically root 2 Vs by 3, that is 0.471. So, this will be the values for the line to neutral voltage. Similarly, we can connect the value for the Y connected load, and so you can calculate, you can substitute the previous values. So, this will be the values for the actually the different phase voltages. Thank you for your attention. We shall continue our discussion from this point from your next class. Thank you.